This is number 56, chapter 8, page 271, and we have a situation where a bullet, and the bullet's moving, let's see here, with a velocity of 1,000 meters per second. It's going to hit this board that's 18 kilograms. The board has a radius of 1 meter from the hinge, distance from one side of the hinge, but the bullet hits at 10 centimeters from the end of the door, which means it's actually 9 centimeters from the hinge. So they got a bunch of questions about that. Uh, the first question is, before the bullet hits the door, does the bullet have angular momentum? You're thinking, well, the bullet's not going in a circle, but actually anything can have angular momentum, because angular momentum is I omega. That's one angular momentum. It's a terrible I. So it's I omega, or for linear things, it's mv r. Okay, so the bullet absolutely, yes, has a mass of 0.005 kilograms. It has a velocity of 1,000 meters per second, and it has a distance from that hinge of 0.9 meters, 9 centimeters. Well, I've already done the math, and that's 4.5, and that's going to be kilograms times meters squared per second. So that's its angular momentum. So yes, it does. The second question is mechanical energy conserved in this collision. It says answer that without calculations. We already know if it embeds into the door, that means that energy is taken away from the bullet as it moves all those wood fibers to the side, and there's heat and sound, and so I know that the initial kinetic does not equal the does not equal the final kinetic, because it's a perfectly inelastic collision. So I already know that it's not, because it's perfectly inelastic. They stick together. All right, C, that's B. C, they ask the question, at what angular speed does the door swing open immediately? Well, that's just L initial equals L final, because angular momentum is conserved, and they do tell us a few things. The door has an moment of inertia of 1/3 mL squared. If I put my numbers in, where m is 18, L is 1, and I divide that by 3, I get 6 kilograms times meter squared. So that is the angular moment of inertia of the door. And so initially, I already know that my initial angular momentum is all bullet, which is 4.5 kilograms times meter squared per second. And then that's going to equal I plus I omega final plus m omega r squared, and that's omega final. So that's basically going to equal I plus m r squared times omega final. All right, and I know m, well, I don't, but I know mass of the bullet times r squared. If I put 0.005 times 0.005 times 0.9 squared, put those numbers in, because remember, it's 0.9 from the door. In other words, the bullet where it hits from here to here is 0.9 meters. So if I put that number in, I get mR squared equal to 0.0041, and that's 4141. All right, that's bugging me. Hold on. 0.0041 kilograms times meters squared. So that's going to equal 6.0041 times WF equals 4.5 kilograms times meters squared per second. So WF is going to equal 0.75 radians per second. That's what they asked for in C. And that is just conservation of angular momentum. It would have been a little more simple if they'd have had, I mean, they have this particle, and so this is good because you do learn that particles can have angular momentum, even though they're not going in the circle with respect to any kind of hinge or pivot point. So that is, answer to C is 0.75. All right, so D, what is D? D is calculate the energy of the bullet, door bullet system, and determine whether it's lead. Okay, so normally, you know, in linear terms, you do a different color here. Normally, K is equal to 1/2 mv squared. But remember, for rotational, K rotational is 1/2. Remember, I is like m, and v is omega squared. So I'll have to do, and this is going to be omega final because they've hit. So all I'm going to do is I'm going to put in 1/2 times 6.0041. I've already figured that out. Okay, that's times omega f, 0.75 radians per second. Square that, don't forget to square that. And when you do all that, you get 1.69 joules. It's not very many joules. And they want to, that is, they want to compare that to kinetic energy before it hit. Well, the bullet is linear before it hits. It's just going to be 1/2 times 0.005 kilograms times V. What is V? V is 1,000 meters per second squared. That equals 25,000 joules. Are you kidding me? That is not even close. This thing lost almost all of its energy when it hit the door. The door was pretty hard and it used up its energy with heat, sound, moving all those little molecules out of the way, so not even close was it conserved. That's how you do number 56. Oops.